referring to. Okay, now let me just give you another example, because this set is open. Okay, so this guy is open here. Okay, so the complement is open, so therefore the set is closed. All right. Now let me just give you another example. So for instance, what about this set here that we're looking at? Is this open or not? Okay, so here we actually we have seen that is not, this set is not open. Okay. Okay. Because what? Because the element 0 does not have a neighborhood in the set. But is it closed? What is actually the complement of it with respect to the set of real numbers? Now what's going to be the complement of it? This is the union of what? This is the union of the set from minus infinity to 0, where 0 is actually not included in there. Okay? And the set here, this one here, so from 1 till plus infinity, right? Okay? Now what about this set here, guys? Is this closed or this, no, so is this open, yes or no? Is that set open? No. Okay, so this is not open. Okay, so this set is not open. Why is that? Because the element 1 does not have a neighborhood in the set. Okay, so in that case, so this set cannot be open. Now if the complement is not open, then the set itself cannot be closed as well. So you can see that it is neither closed nor open, right? So it's not closed either. Okay? So it's neither nor. Okay, so there are 4 possibilities, guys. Okay? Closed but not open, open but not closed, both and neither nor. That's it. Okay? I mean, this is how we defined it. Okay? I'm not saying that this makes sense, but I'm saying that this is just how it is. Okay? All right? You cannot say like half open and stuff. You know, there's no such thing. Okay? If you open a can and it's open, you cannot say it's like half open or something, a bottle or whatever. Okay? So it's open. Right? Doesn't matter. Okay, guys. Good. Now, and this is, now we have to look at certain things. Okay? So, you know what countability is? Still remember from last week? That was a very important definition. And, okay, so a set is called countable if it can be written as a sequence. And then you actually know what a countable union is. So you suppose that you have a countable open sets now. And this is something that's very important. Okay? So I'm going to put this into a lemma. Okay, so this statement is more important than so the union of countable open sets is always open. Okay, so the union of countable open sets is always open. Okay. That's the first statement that I make here. Okay, so this is actually part of the lemma. Okay? All right. But the union of countable closed sets, okay, so this is what I would like to add to here, the union of countable closed sets is not always closed. Okay? So the union of countable open sets is always open, okay, on the one hand, but the union of countable, so this is the first statement here, and this is the second one. So the union of countable closed sets is not always closed. And let me give you an example to that. Okay, so you understand this. Okay. Actually, you've seen that before. Okay, so check it out. So for instance, what I do is this. Okay, so I'm defining the following intervals. Okay, so according to a certain formula, let me just give you the formula first, so then you see it better. Okay, so for instance, okay, so I'm defining the intervals as follows. So here you have a n, so the nth interval will be given by the following formula. So here, -1 plus 1 over n and 1 minus 1 over n. So these are closed intervals. Okay, so the first interval that I'm starting here is actually minus 1 plus 1 equal to 0. Okay, so this is closed. Okay, because the complement of it is open. Okay, all right, so this interval is closed. And the second one would be actually the interval from minus 1 plus 1 over 2 equals minus 1 half. Okay, and this goes from minus 1 half to plus 1 half. Okay, so that is also closed. Okay, so the third one is as follows. You have minus 1 plus 1 over 3 equals negative 2 over 3. So you have negative 2 over 3, and here you have plus 2 over 3, etc., etc. Okay, so this is how it works. And the fourth will be according to that. So this will be the lower bound will be negative 3 over 4, and the upper bound will be plus 3 over 4. Okay, so this is the positive 3 over 4. You understand? So we actually consider that. Now, what happens if you take the countable union of these intervals? So what I'm doing is this. Okay, so I'm taking the countable. So this goes on, and what you would do is actually you would take the countable union of these intervals. So what you would get, you would get, you know, I mean, the intervals are getting larger, right? But one number will never be covered in the interval, and which is what? Yes, exactly. So this will be resulting in the following countable union. So this will be the interval from negative 1 to plus 1, where actually the lower and the upper bound of the interval are not included in the interval itself. So you can see that here. So this is the countable union of closed intervals. Okay, so this is the countable union of closed intervals. Okay, and what you see here in this example, this can be open. Okay, I mean, I'm not saying that. Okay, so I mean, this is open. Okay, so actually it's actually pretty precise, and you can say that this is open. So but the countable union of closed intervals can be open. Okay, as you can see here from this example. All right. So I goes from 1. Sorry, it was not displayed here. Okay, you understand? I mean, we already considered that example. Okay, so actually I defined a set of all closed intervals and a set of real numbers, and we were actually experiencing the fact that, you know, this set was not closed under countable unions. It was only closed under finite unions. Okay, but not under countable unions. See what I'm saying? So, and that's actually quite similar because, and the reason for that is because, I mean, just let me just justify that statement what I was making, is because the countable union of closed interval can be open. Okay, so there is a possibility for that. I'm not saying that this is always the case, right? But it can be the case. Now, the second statement that I would like to make here in this context is that the countable intersection of closed sets is always closed. So, on the other hand, so this will be the second part. Okay, so the intersection, okay, of countable closed intervals is closed. Okay, so this is the first statement that I would like to make here. Okay, so if you're not taking the union but the intersection instead, then you would get that actually the countable intersection of these countable intervals is actually, or closed intervals, is always closed, so no matter what. Okay, so if you take the intersection, then this will be true. Okay, but on the other hand, the intersection of countable open intervals is not necessarily open. Okay, so the intersection of countable open intervals okay, is not always open, okay, or open sets actually, that would be more precise because we were not just looking at intervals, but we were looking at sets, but anyway, okay, so is not always open. And let me just give you an example to that as well, okay. So, and this is, let me just say that this is not only true for intervals, but sets, okay, so you can add this here, you don't have to wipe it out, just you can close sets, okay, because I'm not talking about just intervals, I'm talking about sets in general, and intersection of countable sets, okay, because even the set of real numbers that are actually things that cannot be written as intervals, okay, let's see the set of real numbers, for instance the Vidal set, okay, anyway we'll talk about that later. So let me give you an example to that too. Okay. So suppose that you have, let's say, the following intervals that I'm going to define here. So this will be an, and the definition will be like this. So the nth interval will be from -1 minus, so -1 minus 1 over n. So this is the lower bound of the interval, and the upper bound of the interval will be 1 plus 1 over n. Okay. And now what I'm taking is I'm taking the intersection of them. Okay, so let me start at actually the second part because that is something that, but you can do that here as well. So the first one, it goes from, this is the interval from 0 to 0, where 0 is not included in there. So this is actually the empty set itself. Okay, so the first set is the empty set. Okay, the second interval goes from -1 minus 1 over n equals -1.5. All right. No, I apologize. Okay, so we have we take wait. Okay, so here you have -1 minus 1 over 2. Okay, so this is the second one, and here this is not the empty set, guys. I'm sorry. Okay, so because you have minus here, apologize. So you have -1 minus 1 over n. So if n is equal to 1, then you have -1 minus 1 equals -2. It's not 0. Okay, and 1 plus 1 over n equals 2. Nobody noticed that, right? Okay, anyway. That was just a test, okay? And you failed. Okay, so, no, I apologize. I was joking. But anyway, you failed. You failed. So, and here for the second one, you have -1 minus 1 over 2 equals -1.5, okay, so this is like, here you have positive 1.5, okay. This is the second part. The third interval here, according to this, so this is -1 minus 1 over 3 equals, -1 and 1/2, 1/3, so this is going to be -4/3, and this is positive 4/3, see. And for the fourth interval, you get -1 minus 1 over 2 equals -1.25, this and that. So you have positive 1.25, etc., etc., etc. Okay. All right. So these are the intervals that I'm considering right now, according to based on the formula. And what I would like to do is I would like to take the countable intersection of these intervals. So here it goes from 1 till plus infinity. Okay. So we do this for like infinity many times. Then this thing will become 0, right? So the limit of 1 over n as n approaches infinity will become 0, right? So you have -1 minus 0, and this is actually the intersection that you would get here. So the countable intersection of these intervals will be equal to what? Maybe you can see this here. Okay, so we're getting closer to -1 and 1, and the intersection, but -1 and 1 will be always in there. Okay, so no matter what, the upper and the lower bounds, so -1 and 1, will be always in the intersection, because if it's in the intersection, or if it's actually in all of them, then it's actually in the intersection of them, right? Okay, so if it's all of them, then it's in the intersection of them. So this will be a closed interval that goes from -1 to 1. Okay, so as you can see, this is the countable intersection of open intervals or open sets, and that can be closed. Okay, so this is the countable intersection, which is actually the same thing as of closed intervals, so of open intervals, can be closed, right? You see this? And this interval is closed. Okay? Why? Because its complement with respect to the set of real numbers is open, so anyway, this is what you would get. Okay? Now let me summarize that because that is okay. So if you can read this, countable intersection of open intervals can be closed. Okay, this is what we are having here. Okay, why is this closed? Because -1 and 1 are always in the interval. Okay, there are actually elements in all of them, no matter where you are. Okay, so basically, actually, this is what you get as a result. Okay, so this is an example demonstrating that the countable intersection of open intervals can be closed. I'm not saying that this is always the case. Okay, so please pay attention. This is not always the case, but it can be. Okay, now let me summarize that because that's important. Okay. Okay, so just summarizing it because this is a statement that I would like to make. So a union of countable open sets is always open. Okay, so the union of countable open sets is always open. Okay, and intersection of countable closed sets is always closed. Okay. Okay, but this is just because that is true, it doesn't mean that it could be, for instance, the union of countable closed sets is always closed. So this is not the case. Okay, so but what you have is actually the union. What about the union of finite closed sets? Okay. Now the union of finite closed sets here. Okay, so that's the difference. Here you have just countable. Okay. Okay, but here you have. Okay, so here in this case you just have finiteness. Okay, so finite closed sets is always closed. So if you have these closed intervals and you just take the finite union of them, then what you will get is actually a closed interval. Okay, so finite union, you know what the finite union is. Okay, so finite means that its cardinality is strictly less than that of the real number, of the natural numbers. Okay, so the union of finite closed sets is closed. Okay. And this is not true for countable closed sets. Okay, so not true for countable closed sets in general. Okay. Okay, so there are cases for which it's true, but in general it's not true. And the intersection, intersection of finite open sets, or intervals, open sets is always open. Okay, but let me just remind you that this is only true for finite sets, but not for countable sets. Okay, so not true for countable open sets in general, as we see in this example. So not true for countable open sets in general. Okay. Now that doesn't necessarily mean that the intersection of countable open sets has to be always closed, and I'm not saying that. Okay, but there are cases for which there are. So therefore, the statement that it is actually closed for countable closed intervals is not true in general. Okay. Okay, so this is just a summary. Okay, guys. Now I'm leaving you here. Okay, because I have to hurry. So we stop here. And on Friday, if you have questions, then you can ask me after lecture. I have time to answer all, as much time as you like. Okay. Please do not forget your assignments. Okay. Hope to see you on Friday, guys. Goodbye.